In this PowerPoint presentation, what we are going to do is study about redox reactions. We will be balancing equations using the ion-electron or half reaction method and oxidation number method. The first thing to do is define what is oxidation and what is reduction. The easiest way to remember that is using the acronym OIL-RIG. Oil represents oxidation is loss of electrons, and RIG represents reduction is gain of electrons. Whenever there is a redox reaction that is taking place, there will be an atom or ion that loses an electron. That atom or ion is getting oxidized, and it's a reducing agent. There is a second atom or ion that gains electrons. In the process, it gets reduced, and that's the oxidizing agent. So OIL-RIG kind of tells us what is oxidation and what is reduction. If there is an increase in oxidation number or the valency, then the process is oxidation. If there is a decrease in oxidation number or decrease in valency, then there is reduction. Here are some examples of oxidation. Magnesium loses 2 electrons, changes into Mg2 positive. Therefore, the reaction is an oxidation reaction. Sodium, neutral atom, changes into sodium positive and loses an electron. Therefore, that is again an oxidation reaction. Aluminum loses 3 electrons and changes into Al3 positive. Therefore, that is again an oxidation reaction. The fourth one is sulfide ions. It has got 2 electrons more than a neutral atom. Now what's going to happen here is it's going to lose the 2 electrons and change into a neutral atom with 0 charge. In the process, it lost 2 electrons. So this reaction is also considered an oxidation reaction. Fe2 plus changing to Fe3 plus is an oxidation reaction because it loses 1 electron. Fe changes into Fe3 plus and loses 3 electrons. Therefore, that's also an oxidation reaction. Tin has 2 oxidation numbers, 2 plus and 4 plus. In this case, it's losing 2 electrons to change from 2 positive to 4 positive. Therefore, this reaction is also an example of oxidation half reaction. Here are some examples of reduction half reaction. Chlorine atom gains 1 electron and changes into a chloride ion. Oxygen atom gains 2 electrons and changes into an oxide ion. Therefore, that is also a reduction. Nitrogen gains 3 electrons and changes into a nitride ion. Hence, that's also a reduction reaction. Fe3 positive gains 1 electron to change into Fe2 positive. That's the reduction half reaction. Fe3 positive, if it can gain 3 electrons, will change into a neutral atom with 0 charge. That's again a reduction reaction. So these are some examples of oxidation and reduction reactions. Oxidation number. The valency of an element or the charge of a metal ion or charge of a negative ion are usually considered oxidation numbers. That's another way for representing the valency. We can assign oxidation numbers to elements based on their valencies, where they have completely lost electrons or gained electrons, or depending upon their difference in electronegativities. Therefore, we consider these charges as hypothetically assigned based on a set of rules which will help us in balancing equations using concrete rules. Here are the rules for assigning oxidation number. The oxidation number of an element in the elemental state is 0. What it means is you pick any element from the periodic table, it's got a 0 charge because the number of protons are equal to number of electrons. If an atom loses an electron and gains a positive charge, the positive charge is considered the oxidation number. If it's a non-metal, if it gains electrons, the negative charge is considered the oxidation number. In a binary compound, the more electronegative element is assigned a negative number, and the more electropositive element is assigned the positive number. Even though there is no complete transfer of electrons, the oxidation numbers are considered to be positive whole numbers. In compounds involving hydrogen, the oxidation number of hydrogen is all the time positive 1. However, there are exceptions. The exceptions come in metal hydrides. In metal hydrides, hydrogen is considered to be the negative ion, therefore it gains an electron and has a -1 oxidation number. This should be helpful while trying to balance equations which contain metal hydrides. In compounds containing oxygen, oxygen is always assigned a -2 oxidation number. However, there are 2 to 3 exceptions. If the oxygen containing compound is a peroxide, oxygen has an oxidation number of -1. You ought to know this to be able to balance equations. If oxygen is combined with fluorine, the most electronegative element in the periodic table, oxygen has a positive oxidation number. OF2 is a case where the oxidation number of oxygen is +2. In O2F2, the oxidation number of oxygen is +1. For neutral molecules, the sum of the oxidation numbers is always 0. If I consider carbon dioxide, there are 2 oxygens, therefore the total oxidation number for 2 oxygens would be -4, which implies carbon should have an oxidation number of +4, so that the net charge becomes 0. If it's an ionic compound like sodium chloride, sodium will have +1 oxidation number and chloride will have -1 oxidation number, making it NaCl, 0 charge. For complex ions, the sum of the oxidation number is the charge of the ion. What we mean by that is, if I take carbonate ion, CO3, 2 negative is a charge. Therefore, the total charge of the ion is -2. Oxalate, the formula is C2O4, 2-. The total charge is -2. Manganate ion, MnO4-. The net charge represents the charge of the polyatomic ion. Here are some examples where you can practice identifying oxidation and reduction. Interestingly, the first example is unique. The sulfide in hydrogen sulfide and the sulfide in sodium sulfide, they both have the same oxidation number of -2. Oxygen in sodium oxide and oxygen in water, they both have the same oxidation number of -2. Therefore, this is typically not a redox reaction. Try to identify the oxidation numbers of the different elements in the reactants and products and see if you can identify the part of the reaction that undergoes oxidation and part of the reaction that undergoes reduction. In the next part, we are trying to balance an equation. We're going to use the half cell method or ion-electron method for balancing redox reactions. These methods are very precise and can give you accurate answers, unlike the trial and error method, which you may have done in grade 10 and 11. Rules for balancing, if you look at it, you'll find first thing to do is determine the oxidation numbers of all the reactants and products. Identify the element that is showing an increase in oxidation number. Then you can split up the oxidation half reaction and the reduction half reaction. In this case, you'll find the oxidation number of Fe in the reactant side is +2. The oxidation number of Fe in the product side is +3. Therefore, iron is the ion that undergoes oxidation from +2 to +3, which involves loss of an electron. Manganese in manganate ion. The formula of manganate ion is MnO4-. Manganese is considered to have an oxidation number of X plus 7 times 4. Manganese has an oxidation number of X. 4 oxygens times 2 makes it -8. The net charge of the polyatomic ion is -1. Therefore, manganese should have an oxidation number of +7. If you look at manganese in the product side, it exists as Mn2-. Therefore, the oxidation number of manganese has changed from +7 to +2. Here, there is a reduction in oxidation number, which means manganese in manganate undergoes reduction to Mn2-. For this reduction to take place, we need electrons, and that is provided by the oxidation half reaction. Now, there are two other words that you may want to get familiar with: a reducing agent and an oxidizing agent. A reducing agent helps in the process of reduction. Reduction involves gaining electrons. Therefore, a reducing agent provides electrons. So in this case, iron provides electrons by losing one electron. Therefore, it's a reducing agent. Manganese in manganate ion requires electrons. Therefore, it helps in gaining the electron. Therefore, it's called an oxidizing agent. Oxidizing agent brings about oxidation, and the reducing agent brings about reduction, and it helps in the process by providing electrons and gaining electrons. In the next step, we separate the two reactions as oxidation half reaction. In this case, Fe2+ giving you Fe3+ plus 1 electron, and reduction half reaction, where manganese ions are formed from manganate ion, MnO4- plus H+ plus 5 electrons, giving you Mn2+ plus water. We write water as a product because in one of the reactants we have oxygen. All the time, oxygen in any of the ions will change into water when the reaction takes place in an acidic or basic medium. The final step, you would notice that in the reduction half reaction, which is MnO4- plus H+, we require 5 electrons so that the oxidation number changes from +7 to +2, which means iron has to produce 5 electrons. 1 mole of iron will produce 1 mole of electrons. Therefore, taking 5 moles of Fe2+ gives you 5 moles of Fe3+. So that's the fundamental part where we balance it, making the number of electrons lost equal to the number of electrons needed, and then we add up the equation. Since there are 4 oxygens, it produces 4 moles of water, and when 4 moles of water is formed, we need 8 H+ ions. Since the reaction is taking place in H+ medium or an acidic medium, we can add the right number of H+ ions. Therefore, the final balance equation would be 5 Fe2+ plus MnO4- plus 8 H+ gives you 5 Fe3+ plus Mn2+ plus 4 H2O. That's the way we balance an an equation using ion-electron method or half reaction method. If you have common terms on either side of the reactants and products, the common terms should be cancelled out. Here are a few examples for you to practice. Write down those equations and see if you can balance them. They're all balanced in the acidic medium. pause this portion of the PowerPoint and then you can write them down. Here is another example. Manganate ion, which is oxidizing agent, reacts with oxalate ions to give you Mn2 plus CO2. Here the reaction takes place in an acidic medium, so you can add H positive on the reactant side and balance oxygens with water molecule. One of the key aspects that you should be looking at in this example is whenever there is an element undergoing change in oxidation number, you got to balance those atoms first, then count the electrons that it can produce or how many electrons it can accept. So in this case, C2O42 negative is the oxalate ion. There will be a change in oxidation number for carbon and oxalate and carbon dioxide. Since there are 2 carbons in oxalate ion, the first thing to do would be to produce 2 moles of carbon dioxide. Count the oxidation number for 2 carbon atoms in the reactant and product side, then produce appropriately the number of electrons that you need. So that's the care that you should take while trying to solve this equation, which is being balanced in the half reaction method or ion-electron method. This is the next method. It's called oxidation number method. It can be applied quite frequently in most of the reactions that you use if you identify the oxidation numbers. Here the molecules will be complete neutral molecules, unlike in the previous case. The first thing would be assign oxidation numbers to all the elements in the equation. Identify the atoms which undergo change in oxidation number. Determine the ratio in which these atoms must react so that the total increase in oxidation number equals to the decrease in oxidation number. When you multiply them by coefficients, those will actually make the number of electrons lost equal to number of electrons gained, and then you can balance the rest of the equation by inspection. So here is an example. HNO3 reacts with hydrogen sulfide to form nitric oxide, sulfur and water. First we determine the oxidation number of nitrogen in nitric acid. It's given as +5. In the product side, nitrogen changes into NO, where the oxidation number is +2. What it implies is oxidation number decreases from +5 to +2. Therefore, that is a reduction half reaction. Now, the next element that really shows a change in oxidation number is sulfur. Sulfur in hydrogen sulfide has got an oxidation number of -2. Sulfur in the product side has an oxidation number of 0, which means when sulfide changes into sulfur, it's going to lose 2 electrons. So that is the oxidation half reaction. So you will see that nitrogen, when it changes into NO, requires 3 electrons, and sulfide, when it changes into sulfur, produces 2 electrons. Now, if the equation has to be balanced, the number of electrons needed should be equal to the number of electrons produced. When these numbers are odd number, as in the case of nitrogen, and even number, as in the case of sulfur, you make it a whole number which is even by multiplying it by 2. So 3 times 2 makes 6 electrons, and 2 times 3 makes it 6 electrons. Therefore, if you're multiplying nitrogen by 2, 2 becomes the coefficient of HNO3, and if you're multiplying sulfide by 3, the coefficient of H2S becomes 3. The rest of the atoms are balanced by inspection. It is a relatively easy method to do this balancing. This slide again is an elaboration of what was stated right now. Once you put the coefficients 2 and 3 for nitric acid and hydrogen sulfide, you get 2 moles of nitric oxide, 3 moles of sulfur, and since appropriate numbers of oxygen atoms are there, they have been changed into water because we have hydrogen sulfide which produces the hydrogen for it. Here are a few examples where you can test out your oxidation number method balancing. pause this part of the video, write down the examples, and then verify if you have got the right answers. Answers to the previous questions are given here. Pause it, write it down, and then proceed. And that's how we balance equations using oxidation number method and ion electron method. Hope this was helpful.